Welcome back to the third session of this Swayam course. I would like to start off by making another note for teachers who might be watching the Swayam course. And this comes from a question that I have been asked very often when I have conducted faculty development programs in this very room in the Teaching Learning Center here at IIT Madras. I have been very often said that I are told explicitly by teachers who work in various universities, polytechnic institutions and so on, that the active cooperative learning seems to be a very nice technique. However, achieving the goals of ACL while also honoring the university requirements, particularly the syllabus completion requirements, can be a challenge. I agree, that's a challenge. One way in which I can think about a creative solution to this problem is by basically giving some onus to the students for their own learning as well. And this is very important to the principle of andragogy. By that what I mean is we are dealing with very often adults in a university setting, so we should make them owners of their own learning. So one thing that can be actually done is use ACL in order to set the framework, the scaffold for the lesson that needs to be covered as prescribed by the university, and not necessarily spend a lot of time describing everything that is there in the syllabus, but spending a lot of time trying to establish the cornerstone ideas and then providing guidelines to the students, and also providing framework so that the students can introspect and also self-correct, do course correction and so on and so on. So that might be a much more efficient way of integrating ACL into our classrooms. So to summarize, what I believe might be reasonable is to certainly take lessons from active cooperative learning as a principle, as a practice, as a philosophy, and enhance the efficacy of our teaching, and not get too caught up by content coverage, but sort of step back and ask what are the cornerstone ideas as far as this content is concerned, and focus on cornerstone ideas as far as the classroom experience is concerned. So I will probably give you an idea of scaffolding here in this particular session. And not only that, in the last session I was also supposed to have a graphing exercise, and we sort of ran out of time, but today we will certainly look into graphing as an exercise that can actually facilitate student learning as well. So this is the note that I intended to give university teachers and so on. So a quick recap, if you recall, all of you recall that these are what you yourself said were the summaries or were the points that summarized the last session. Briefly, we looked at what classification means and how classification can be important in any academic discipline for that matter, to basically consolidate information in a very structured manner. And then we looked at some classifications of materials. We did not look at all classifications of materials. We basically described metals, ceramics and glasses. We did not go much beyond that. But I did give you some homework. So if you can actually give me the outcomes of that homework, if you have looked for information, that will be relevant. So I remember that I asked you to look at thermal and electrical conductivities of a wide range of materials. So maybe ceramics, some ballpark values, metals, some ballpark values, polymers, again some ballpark values. So if you can give me some numbers, that will be nice. So typically the thermal conductivity is represented by sigma. Now this can be a little confusing, isn't it? Because in the last class I used sigma for describing stress. So just to make a distinction, I will call this elec. So this basically is the symbol that we will use in this particular course for electrical conductivity, and then kappa is going to be used for thermal conductivity. So this is what we will be using for electrical conductivity. And this is what we will be using for thermal conductivity. So can you give me some values? I am sure you would have seen some databases and so on. So maybe for ceramics, some values, okay. Metals, some values, maybe polymers, some values. How many of you had a chance to actually look at these values? If you have not, maybe I'll give you a minute or two to use internet and then find this ballpark numbers, okay? And 1 second. And you will have to give me units in every single case. All right? Yeah. So for metals it is 10 to the power of 10 to the power of 7. So Siemens is also called ohm inverse or mho. All right. So I will write it. So this can also be mho meter inverse, right? So this is Siemens or mho meter inverse. Very good. So did anybody get the values for ceramics?
10 power minus 9.
Ah, wow. See how different it is, isn't it? So it's, let's say, 10 to the power of minus 9 units.
Same.
Siemens per meter. So how different are these powers? 10 to the power of 16, right? So there are cases wherein this ratio goes up to 10 to the power of 20 and more. So if I look at the conductivity of the best metal, let us say I look at conductivity of gold and I look at the conductivity of the worst ceramic, let us say of quartz. So why don't you give me those two numbers? Spend some time looking at your search engines. Okay, you want to give me silver's sigma. All right, please. Huh?
6.8.
10 to the power of 7 Siemens per meter. Now that's similar to what you have given, right? 10 to the power of 7 Siemens per meter. This is also about right. All right. And then,
And copper.
okay, you want to give me coppers also, okay?
6 into 10 power 7.
10 to the power of 7 Siemens per meter, fine. Now let us look at some ceramics, all right? So let us say quartz.
So,
What is the value?
10 power 7.
Quartz? Electrical conductivity. So this is electrical conductivity. 10 to the power of minus 18 Siemens per meter. Wow, look at this. So the ratio is 10 to the power of 16, right? And let us say alumina. Can you look at alumina? Al2O3. Ten to the power of
180. It's not like 8. 10 to the power of minus 18.
this 10 to the power of minus this one alumina.
So the quartz is 18. 10 to the power minus 18.
Wow, 10 to the power of okay, all right. So if you take the ratio, it is 10 to the power of 25. Incredible, isn't it? A physical property varying over 25 orders of magnitude. Amazing, isn't it? 10 to the power of 7 here, and here is 10 to the power of minus 18. Okay, alumina. This is 10 to the power of minus 12 Siemens per meter. All right. So, of course, the lessons learnt is, what is the SI unit of conductivity? Siemens per meter. For ceramics, the conductivity can be as low as 10 to the power of minus 18 or even lower. In the case of alumina, it is 10 to the power of minus 12. If you take the ratio between the conductivities that are observed for metals and semiconductors, it can be as high as 10 to the power of 25. You can see that. And in fact, there is no physical property which in SI units actually spans such a wide range. There is absolutely no other physical property, whether it be specific heat capacity or thermal conductivities and so on. Nothing basically spans this extraordinary range of values like electrical conductivity does. So electrical conductivity in the world of materials offers the widest window, okay, where the electrical conductivity is measured by using SI units, where the properties are measured in SI units. Okay, this sort of gives you the widest window. All right. So let's look at thermal conductivity now for the same materials. So silver.
Silver is like 419 watt per meter.
419
Watt
meter Kelvin. So what is the SI unit of thermal conductivity? Watt per meter Kelvin. Very good. So this 419 for copper.
Copper is 385.
385. So not that different after all. Okay. Now for quartz, so why don't you also look for some numbers? Let's give people 1 minute. You spend some time. You can distribute the load. One of you can do quartz, the other person can do alumina. Thermal conductivity. Yeah. Let people spend some time. It's good to know how to use search engines to gather information. 32 units? Watt per meter Kelvin. How much? What is the value? 32. Very good. So this one is 32 watt per meter Kelvin. What about for quartz? 37. Close, right? So you can see that the thermal conductivities of metal is 10 times higher than the thermal conductivity of metals is roughly 10 times the thermal conductivities of ceramics.
Ranging from 550 to 400.
Right. Similarly, I told you a thumb rule last time about tensile versus compressive strength about ceramics. What did you see last time in the last class?
More as compared to thermal conductivity.
What is that?
Electrical conductivity is more as compared to thermal.
Oh, much more. But you see, the units are different. Here it's watt per meter Kelvin. Here it is Siemens per meter. So in Siemens per meter, silver and copper, you can see they have very high electrical conductivities. 10 to the power of 7 Siemens per meter with some prefactor. All right. Quartz, it's very small, 10 to the power of minus 18. All right, and look at the ratio. It's going to be 10 to the power of 25, right? But here, if I look at the ratio of the thermal conductivity here and here, the thermal conductivity of metals is higher, and it's roughly 10 times higher than the thermal conductivity of ceramics. Did you notice that? Likewise, in the last class, I told you something about the strength. So, compressive strength of ceramic versus tensile strength. Which one is higher? Compressive strength or tensile strength? Compressive. And by a factor of?
4,000.
By a factor of?
That was less than 400, it was 5,000.
kind of.
So how different are the values? By a factor of 10? Yeah, it's different by a factor of 10. So what is the typical tensile strength that you saw?
500, 400
In units, megapascals. Okay. Compressive?
That is 5,000.
5,000. And what about Young's modulus?
That is gigapascal.
It's in gigapascals, right? How many gigapascals?
450.
So a few hundred gigapascals. So roughly 1/100th of the Young's modulus is the tensile strength. Is that correct or wrong? 1/1000th, correct. And 10 times the tensile strength is the compressive strength, roughly. So these are thumb rules that you might actually benefit from. Alright, so shall we also do the similar exercise for polymers and semiconductors? Because that will enable us to go through the write-up very easily. Alright, so spend 1 or 2 more minutes, discuss with one another. You can load share. Some of you can do for polymers, okay? So some of you can do for polymers and some of you can do for semiconductors. You can do for polymers, semiconductors, but then tell me the numbers together. Alright, so let me, so remember there are a wide range of polymers. So polymers and semiconductors. Please spend some time looking at the sigma and kappa values for polymers and semiconductors.
Polymer is 2.23.
No, you write down and I'll come around. So, but all of you understand what you are expected to do, right? Good. So, a characteristic of semiconductors is that their conductivities again vary by a wide range. And in fact, semiconductors can have tunable conductivity. For example, silicon versus doped silicon. Doped silicon can have very high conductivity when compared to silicon. So look at, let us say, N-type silicon, P-type silicon, just silicon. You understand? Similarly, let us say some semiconductors that are other than silicon. And I have given some semiconductor formulae here. Gallium arsenide, gallium phosphide, indium phosphide, indium arsenide, silicon carbide, silicon. So you can choose 2 or 3 of these. And then when they are N-type, what is the conductivity? When they are P-type, what is the conductivity? Intrinsic, what is the conductivity? You can take any one material and tell me the values, okay? Because that will give you an idea of why semiconductors are so widely used for electronics. And the reason is because you can actually tune their conductivity by a wide parametric window. over a wide parametric window. So what are you all doing now? You are looking at the thermal and electrical conductivities of polymers, correct? So you'll have to tell me what the polymer is. That's okay. So polymer, both thermal and electrical conductivity. Similarly, semiconductors. For semiconductor, you'll have to tell me the formula. You can choose one of these formulas that I have given. All right, and then you can tell me the thermal and electrical conductivity. Ideally for doped and undoped cases, because that will be interesting. So, do you have the values?
Yes, sir.
Huh?
Thermal
Okay,
conductivity.
very good. So, polymers, you can tell me the electrical conductivity first. Typical values.
Thermal conductivity.
Okay, thermal conductivity, tell me.
PTFE is 0.25.
So, for PTFE, that is something called polytetrafluoroethylene. Very good, yes.
0.25 watt per meter
0.25 watt per meter
Kelvin.
Kelvin. Very good. Now, compare that with the earlier value. Earlier, what was the value you got for ceramics?
Ceramics, it was like 32.
32. So, ceramics was a good 100 times better than polymers as far as thermal conductivity is concerned. And metals was 10 times better. So, polymers are 1/1000th as good thermal conductors when compared to metals. Okay. Ceramics are just having a thermal conductivity that is 1/10th that of metals in SI units, yeah. And then if you consider polymers, it's very fractional, 0.25. So now can you put some reason to that kitchen experiment that I told you? You know, you can use kettles, okay, but to prevent burning, you can use plastics. And the reason is because plastics are insulators. Their thermal conductivity is 1/1000th the thermal conductivity of metal. So they don't conduct heat, and as a consequence they protect you, right? So very good. Now let us also write down the thermal conductivity and the sigma Elec value.
Less than 10 power 12 Siemens per
Less than 10 to the power of minus 12
Siemens per.
Siemens per meter. Okay. So would you consider them to be insulators or conductors? So conductors are like metals, no? 10 to the power of minus 7. Polymers are a little bit like ceramics, you see. They conduct only moderately. All right. The worst conductors are about 1/1000th, or they are the worst conductors here, right? The worst conductors here are still much better than the average polymer. See, it's still a million times better. Ceramics, you see, you have a value of 10 to the power of minus 18 to 10 to the power of minus 9. It's a very wide window, correct? Now, polymers, you will find that this is by and large the window. But then there is a category called conducting polymers. Why don't you look for the conductivity associated with a conducting polymer, just any conducting polymer. There are a wide range of conducting polymers. They are called PANI, for example. There is polyaniline, polyacetylene, and so on. So take a look at the sigma values for the same. Is it clear to you what I am asking? So there are a category of polymers called conducting polymers. Let us look at the sigma Elec, that means the electrical conductivity measured in Siemens per meter or mho meter inverse. Do you have some number? Just any number. It could be for any of the conducting polymers out there.
It's like 3.20 into 10 power minus.
Yes. Tell me. 3.25 into 10 to the power of?
Minus 5. Siemens
Wow. Look at that.
centimeters per meter.
Huh?
Siemens per centimeter.
So can you convert Siemens per centimeter into meter?
Minus 3. Minus 3.
Compare this, 10 to the power of minus 12 with 10 to the power of minus 3. So it's a billion times better than other polymers. And in fact, it is much better than most ceramics. So there is this interesting class of polymers which has a billion times higher electrical conductivity. Right? The typical polymer has an electrical conductivity of 10 to the power of minus 12 Siemens per meter, This one has 10 to the power of minus 3 Siemens per meter. It's a billion times higher. It's tremendous. Okay, and it might be interesting for you to actually think how this is possible. How can you change a polymer so that it has a billion times more conductivity? It's very dramatic, isn't it? In fact, it's better than almost all of those ceramics. The only thing that it is not better than is metals, correct? Now, let's have that number out there and let us look at the sigma elec value for semiconductors. Look at the electrical conductivity values for semiconductors. So, this is for polymers, okay? This is for polymers. Now, I am going to write sigma elec here. So, for any of these compositions, so you can look at the semiconductor compositions on the board, gallium arsenide, gallium nitride, indium phosphide, indium arsenide, silicon carbide. They are all in fact called compound semiconductors. Then there are what are called as elemental semiconductors, silicon, germanium and so on. Okay.
Gallium arsenide, it is 52 watt per meter.
So, one second. So, that is comparable to any other ceramic, correct? Because the thermal conductivity of these compound semiconductors is comparable to whatever you found for ceramics. So, no surprise there. Alright. Now, let us look at the conductivity values. For gallium arsenide, let us say intrinsic, p-type, n-type. You understood? So, why don't you discuss it? Show one another your numbers that you are getting. Please discuss with one another. You can choose your own compounds. It can be gallium arsenide, gallium nitride, indium phosphide. All of them have a property called band gap, by the way, that can vary quite a bit. Yeah, you write down. I'll ask you. You understand the question, right? It's very straightforward. The question is electrical conductivity for a semiconductor, its intrinsic type and NNP type. So, there is the intrinsic type is the pristine semiconductor, absolutely pure. Yeah. See, that is very dramatic, isn't it? For gallium arsenide, you have, so that's something that I want you to register. So, it can be as little as 10 to the power of minus 8, as high as 10 to the power of 3 Siemens per meter. So, it is somewhere between a metal and a semiconductor. It is much better than the best ceramic, okay, but it is not nearly as good as a metal. So, it can be 10 to the power of minus 3. So, these polymers, can you call them semiconductors? These conducting polymers, can you call them semiconductors? Look at the, absolutely. So, can you have polymers that are semiconducting? The answer is yes, indeed.
In fact, I saw some polymers they are using for water splitting.
Yes, that's right. So, absolutely anything that you can use a semiconductor for, you can in principle use these conducting polymers, semiconducting polymers. So, they are not really conducting like metals conduct, but they conduct more like semiconductors conduct. Okay. So, that is interesting, isn't it? So, what are the values? Let us say for gallium arsenide, what is the value that you found? 10 to the power of minus 5 to minus 8 to 3 Siemens per meter. Wow, that is a huge window, isn't it? So, there is no other material that shows this 10 to the power of 12 ratio between the highest conductivity that it can show and the lowest conductivity. That is the special thing about semiconductors. Semiconductors, their conductivity can be tuned over a very wide range. Here, you are tuning it over 10 to the power of 11, 10 to the power of 12, basically 11 orders of magnitude, 10 orders of magnitude, Can you look at the sigma Lx for silicon? So this for gallium arsenide. Silicon, what is it? -4 to, yeah, Siemens per meter to how much? 2.2 Siemens per meter. So this also is basically over 10 to the power of 4, right? So it's very huge. So you can modulate the electronic conductivity, the electrical conductivity of these semiconductors. That's really what makes these semiconductors very special. In fact, that is what enables us to use them for a wide range of applications in microelectronics, nanoelectronics. The precise details we can discuss later. But without this ability to modulate the electronic conductivity of semiconductors, it wouldn't be possible to build microelectronic devices, including things like diodes, transistors and so on, nanoelectronic devices, optoelectronic material devices and circuits and so on. It just wouldn't be possible. In fact, even laser diodes, LEDs, photodiodes, all of them are enabled because of this ability of semiconductors, because semiconductors have this tunability. Okay. Polymers and elastomers, I will just give you 2 minutes to go through. Alright, I am not going to describe anything, but look at these polymers and elastomers and always compare it with the other classes of materials. As far as the Y is concerned, the strengths are concerned and so on. Okay. The machinability, the castability is concerned, compare it with metals and ceramics, for example. Alright. Let's say impact strength, is it relevant? Think about it. So I hope all of you have made some numbers, made note of these numbers, because these are relevant. And last time I just mentioned high, low thermal conductivities, but today we put numbers, and you can see how important numbers are. So from now onwards, whenever you talk about parameters, talk about it quantitatively. You understand? Now that you have done some silent reading, you can discuss with one another. Okay? Saurav, you can discuss with one another, identify highlights and compare with ceramics and metals. Okay? That is very important. Say you get some toughness value or Young's modulus, whatever it be, compare it with ceramics and metals. So the first things I would expect you to look at is strength, right? So are polymers considered strong materials? No. Not at all. So under tension and compression, what are the values?
10 to 120 under the.
Yeah, so you have 10 to 120. What's the unit? Megapascals. What was the corresponding value for ceramic? 500. So under tension it was 500. Now here under compression, what is the strength? 350. What was the value there? 5000. So clearly polymers are pretty weak. It is consistent with our daily experience, isn't it? Polymers are pretty weak, you know. Alright, are they castable? Can you quickly cast it in various shapes? Yes. Absolutely. Polymers are easily castable, maybe even printable. Okay. In fact, increasingly people are thinking about printed electronics based on plastics. So printed electronics is also called plastic electronics. People are thinking about printing and casting, you know, into various shapes. Printing electronic devices, going away from typical fabrication and thinking about printing. All right. Okay. Next, what is the other thing that you are thinking about? So melting points. How does this melting point compare with the melting point of a ceramic? 10 times lower, right? 10 times, something like when taken in degrees Celsius, you have to always convert into Kelvin, and still, if you still do that, again it's about 10 times different, right? Next is heat capacity of ceramics and metals is comparable. Densities of ceramics and metals are comparable. Polymers, are they dense? No, you are wearing your t-shirts, right? This is made up of polymer. Does it weigh heavily on you? No, it's actually pretty light. So it's a low density material. What are the typical densities? 1 to 2 gram per centimeter cube. And for metals and ceramics, what will be the typical densities?
2 to 17 grams per.
Yeah, so it can easily be 2 to 17 grams per centimeter cube. So it can be substantially more dense, right? And what do you think about the impact resistance of polymers? It's poor. Very good. Similarly, the wear resistance, corrosion resistance can be a little moderate. Okay. Sometimes corrosion resistance can be very low. So the conducting polymers that I was telling you, they tend to have very poor corrosion resistance. Most of the polymers can have fairly moderate corrosion resistance. All right. So corrosion is something that is usually taught under the label of materials degradation. All right, something that we will probably look at in due course, not immediately, but it is important for you to make a mental note of the fact that polymers have moderate resistance to corrosion. Liquid crystals, it's an interesting category of materials. Have you heard of liquid crystals anywhere? LCDs, liquid crystal displays, right? So these are very special class of materials. I won't discuss this in class, so it's going to be your search engine exercise. All right, search engine exercise. So I'll ask you about liquid crystals in the next class. So they are somewhere between crystals and liquids. Typical liquids do not have crystalline order. Liquid crystals, on the other hand, actually have crystalline molecular order, and you might want to see why it is so. The chemistries of these are interesting. So for those who are watching this SWAYAM session, this is an example of scaffolding. You are giving them just enough hints to get them excited and giving them some keywords so that they can go and study on their own as well. And when they come back, you examine them on that particular off classroom learning that they have done. All right. Okay. So next class of materials, they are called composites. So what do you understand by composite? Yes. So composite is actually a combination of otherwise usually disparate materials. So for example, a ceramic and a polymer. They are very different from one another, but you mix them in order to give rise to a composite. Two different ceramics that are very different from one another, you mix it, and with the hope that when you mix them, you are able to actually get properties somewhere between these two materials. All right. So those are composites. So again, spend some time reading about composites. And when you read about it, think about the composites that you might be having around you. Do we have composites around us? In fact, composites are an extremely important class of engineering materials. So please discuss with one another, talk to one another, yeah. So what do you understand by composites? Can you tell me some examples of composites around you? Are there composites in your cell phone, on your body? Huh? Okay, why would you say that is a composite?
Instead of cotton and nylon.
Okay. Yeah, so it's essentially having two different polymers, right? Huh? Concrete is a very good example of a composite because it contains two or more distinct faces, right? Two or more distinct faces. And the hope of combining these different faces is to actually get an emergent property that is probably somewhere between these two properties. All right. So concrete is a good example of composite. And I want you to focus on some of these lines. A large number of modern day materials, including aerospace materials, aircraft materials, etc., are composites. All right. And I've given an example of composites that are obtained by reinforcing rubber. This is again very important because rubber is also an important engineering material, and rubber as is not usable. It doesn't have good corrosion resistance, it doesn't have good mechanical properties, it tends to be extremely deformable and so on. But you add Kevlar into it and you will see the word there is aramid. Okay, aramid stands for aromatic amide. So you add a little bit of Kevlar and the properties of rubber improves. Similarly, rubber can actually be made to undergo something called cross-linking, vulcanization. Over and above vulcanization, you can add Kevlar. So these are methods by which people have been able to render a material that is otherwise not easily usable for industrial applications, engineering applications. They have been rendered useful. All right, and making composites as a consequence is a very big part of what material scientists do. All right, so now is the last category as far as our discussion is concerned. Okay, so please spend time reading about nanomaterials, the definition of nanomaterials, what they constitute. So there is one number there that is very important. Pay attention to that. Okay, so if you please explain to one another what nanomaterials are. All right, so explain to one another and then I will ask one of you to explain it to me. So please discuss with one another. So and think about whether there are nanomaterials around us. Can there be nanomaterials in the biological world? Do you understand what is written? So could there be nanomaterials in this cell phone, for example?
Yeah.
Okay. Could there be nanomaterials inside your body? So nanomaterials are typically having at least one characteristic dimension smaller than 100 nanometers. Alright? So one characteristic dimension. So you take an object, it can have typically 3 dimensions, at least one dimension should be less than 100 nanometers. To get a sense of how small this 100 nanometers is, let me tell you one data. The breadth of your hair is about 100 micrometers. If you have very healthy hair, it's about 150 to 175 micrometers. Alright? So let me write that number down. So the breadth of your hair is between 100 to 175 micrometers. So this is basically 100 to 175 into 10 to the power of minus 6 meters. For your hair to be a nanomaterial or to make a nanomaterial out of your hair, how many times should you actually slice your hair? 1000 times. So your hair is sufficiently small, right? It's already, its breadth is sufficiently little. But along the breadth, you have to actually chop it 1000 times to actually get down to the size. Okay, 1000 times. Now there are people who actually make particles that are much smaller, maybe 2 nanometers, 3 nanometers. Here in IIT Madras itself we actually make. Alright, so that's basically not just 1000, it's 1 divided by 50,000 times, because that's really what it needs to actually get down to 2 nanometers, 3 nanometers. So you take your hair along the breadth, you basically chop it several times along the length, so that the breadth basically continuously decreases. When you are doing that chopping 1000 times, 50,000 times, that is when you are actually entering the nano regime. So these are fairly small particles. Do you think you can see these particles? Certainly not. In fact, you can show this mathematically also. There is a physical argument for this. So the human eye responds to the visible range. Okay, the visible range is between 400 to 700 nanometers. So this is the visible range. This visible range is entirely defined based on our experience of colors. The human eye sees this, blue to red. Okay, so that is basically this 400 to 700. So you can show that the human eye can see a maximum of, let us say, 0.1 millimeters in practice. In practice, it can see about 0.1 millimeters. But if the human eye was a microscope, it would see down to 200 nanometers. Okay, so that is called the diffraction limited length. But the human eye never sees that. The human eye doesn't even see 700 nanometers. The human eye sees something like 1000 nanometers. So our eye is not a microscope. Okay, our eye is not a microscope. But if it was, then we have a diffraction limit and we would be able to see down to 200 nanometers. What you say is not 200, what you see is 5 into 200, 1000 nanometers. That's not true either. So I'm talking about 0.1 millimeters. 0.1 millimeters is basically 100 micrometers. So what the human eye sees is much lower than that, right? Because if the human eye was a microscope, it would be lambda by 2, so that's 200. But what the human eye sees is 1000 micrometers. So that's basically 1000 times higher than that, and right? So substantially larger. Okay, very good. So nanomaterials, why would it be interesting to make these small particles, these small materials? And I asked you, do you have nanoparticles around you? You said that your cell phone has nanoparticles. Where is nanoparticle hidden in your cell phone? Batteries, very good. Batteries, very good. Surface coatings that are used are very often nanoparticles. Yes, very good. So, although currently the kind of surface coating that is actually used to make it water resistant, hydrophobic coating, tends to again use nanoparticles, alright. Okay, so what about nanomaterials in the human body? Do you have nanomaterials in the body? Bones, anything that actually has emergent structure very often tends to have nanomaterial components to it, alright. Can you have nanomaterials in your cells, in the cells of your body? Like what? No, but those are not nanomaterials, those are molecules. Those are molecules. What are the typical dimensions of a molecule? Let's say hydrogen molecule. Hydrogen bond length. About a few angstroms. So you are off there. All right. You understand? So good. All right. So this is important. Sometimes when you get down to these nano regimes, you can enter into size windows where there can be a dramatic change in the optical and electrical properties, and this very often is rationalized by using something called quantum confinement. All right. And likewise, when you go down in size, catalytic properties basically get amplified as well, and that has to do with the fact that when you go down, the size per unit volume basically increases. It's called the specific surface area. So I have an exercise for you, and this will be a classroom activity. You consider a particle to be a sphere, plot surface to volume ratio as a function of radius. Plot it. So surface to volume ratio, and this one is something called specific surface area. This is called specific surface area. Actually, mass per unit area. So let me just correct myself here. This wouldn't be specific surface area. It's just surface to volume ratio. It's just surface to volume ratio. So surface of a sphere is what? Formula 4 pi r square. Volume is 4 by 3 pi r cube. So what is S by V? 3 by r. So I am basically asking you to plot 3 by r as a function of r. How will it look? So the smaller the particle, higher is the surface per volume, right? And this is in fact why people in catalytic science, they use nanomaterials so often. Because when you go down in size, you have so much surface for any given unit volume, and as a consequence you can accelerate reaction rates and so on and so on. You understand? Okay, very good. So we will now conclude with a classroom activity. So I would like you to discuss the summary of the last session, number 1, and one per table will actually summarize the session for us. Okay, number 1. And number 2, this is a homework. Think about making a list of applications for polymers and nanomaterials. That's B question, right? Is a homework for you. All right. I'll convert this classroom activity into a homework. And we still have not gotten to the graphing exercise, so we'll get to that maybe next session. And this is sort of a graphing exercise, right? I asked you to actually derive, plot S by V as a function of R, and as a consequence we rationalized a certain application, namely catalysis. Okay, and found a reason why nanomaterials are used in catalytic science as a consequence. So this is a graphing exercise. In the next class I will give you a graphing exercise on tensile stress test. The homework is you basically identify a bunch of, let us say 5 or 6 or any number of applications for nanomaterials and some applications for polymers. And you can get creative, you can come up with your own plausible applications based on the properties. Now you please help me summarize this session. So the content summary, and then I will give a summary for the teachers, and then we are done for this session. Yes, content summary please.
So we have learnt about semiconductor and stuff.
Very good. We learnt about electrical and thermal conductivities, right? Did you learn something about the SI unit? What is the SI unit of electrical conductivity? Siemens per meter. It's also called mho per meter, right? And what is the SI unit of thermal conductivity? Watt per meter Kelvin. What are the typical values for metals? Values for metals, ceramics, semiconductors. Yeah. So can you remember the typical value for metal? Let's say for electrical conductivity. Very good. So it's 10 to the power of 7 in SI units, right? Yeah. For ceramics, what was it? 21 minus 21 to 10 to the power of how much? 1, 2, 3 minus Yeah, so minus Siemens per meter. All right, and semiconductors, what was the value? 10 to the power of minus 3 to 10 to the power of 8 Siemens per meter. Very good. So these are the values for what? Electrical conductivity, right? Electrical conductivity. And then likewise you looked at typical values for thermal conductivity and also looked at the Young's modulus, correct? And then you also looked at the strengths. Do you agree? Yeah, you're right. So, and then thermal conductivity, Young's modulus and strength, right? For polymers, ceramics and metals. And then you also looked at composites and nanomaterials. Composites and nanomaterials. So now I'll also summarize for the teachers who are viewing this SWAYAM session. So I started out by talking about the challenge associated with combining ACL approach with the university regulations, which very often require completion of syllabus. And I said it might be a good idea for us to actually use a scaffolding approach, spending time doing ACL in the class to clarify some concepts and then enabling the students by doing so and providing sufficient reading material and following up through exercises, quizzes and so on. That might be the right way to actually achieve the university requirement while also ensuring that we use ACL in our classes, all right. And with that and also the additional pointers that I gave regarding, let us say, large classroom settings wherein it might be a good idea to decentralize the learning and enable learning through groupings that are done in a very specialized manner, in a very goal oriented manner. You might be able to still manage large classes. So those were the two things that I wanted to communicate in today's session over and above the content that we discussed. So with that, the session is over. Thank you very much and we'll be back shortly. Thank you.